higher lying electron will carry the rest of the excess energy out as kinetic energy, and you got this OJ process. Both of them can de-excite this core hole, right? So there's two ways to fill this core hole. Okay, so why worry about this? Why study the core hole at all? You may ask, because, well, you know, the core is useless because the core electron, we know, does not involve bonding, right? As our example show in the water molecule, right? All the binding occur, right? In here, all the bonding occur in the valence electron. I mean, the connection between oxygen atom and hydrogen atom, these are MO molecule. MO diagram of this, right? Molecular orbital diagram. Down in the core hole is 1A1. It's essentially atomic light, so there's no, you know, no binding involved. And so what's the big deal? Why you worry about this? Because that should be just atomic light. Okay? But in the late 60s, the Swedish group by the name of Kai Sidborn discovered that, well, you should worry about this because the core hole, the ionization, the location of the core hole, depends on the molecular field, right? So even though okay, so let me go back to this water example. Even though this guy, the oxygen 1s orbital, is sitting alone, it can feel how the rest of the field affects it, right? It can feel the rest of the molecular field. It's very much like NMR because you have spin. The spin can feel the other spin in its own molecular environment. Okay, and so he discovered chemical shift. So he discovered this idea of chemical shift. And let me explain to you how this works. So you have this is our data, one of the data that collected by one of my former students at the synchrotron. So we use at the synchrotron, you have flexibility of choose any photon energy you want. So we choose 340 volt electron volt photon. And we study a series of molecules. We study dichloroethylene, right? Dichloroethylene is a carbon-carbon double bond. And then two chlorine atoms like this, right? So these are the molecular structure. So we look at the isomer of dichloroethylene. So here you have a cis, right, on one side. You have a trans isomer and iso, both of them on left or right. And then finally we look at trichloroethylene, right? Trichloroethylene, as a story, is the stuff that Starbucks used to use to decaffeinate your coffee, right? So it's and then they stopped doing it because they discovered that trichloroethylene is actually carcinogenic. So now they stopped doing it. So for a while, to drink decaffeinated coffee is actually very dangerous because you are using this chemical to decaffeinate your stuff. So it's not a good idea to drink decaffeinated coffee. Now they stopped using these kind of chemicals to decaffeinate the coffee. So what happened? Well, so we look at the full electron coming out from the deep core hole. We look at carbon 1s electron coming from any of these carbon atoms. It doesn't come from these. We choose the carbon 1s. So carbon 1s occur at around 290 electron volt. And so what happened in here? So Sidborn's idea of chemical shift is really exhibit here, right? It's really demonstrated here. Here you have cis and trans molecule, right? And you can see that this carbon atom is surrounded by one carbon, one chlorine, and one hydrogen. Same with this one. One carbon, one chlorine, one hydrogen, right? So they should occur at the same place because they should not occur at different energy, right? Because the chemical environment is the same. They are mirror image to each other. Same with the trans molecule because this is surrounded, same thing. They are mirror image of each other. The immediate molecular field is the same. So you would expect the binding energy should be the same, right? It should be around the same. However, if you look at isodichloroethylene, They are different because this atom, right, the carbon atom, is surrounded by one carbon and two hydrogen. This one, on the other hand, is surrounded by two chlorine atoms and one carbon. And according to Seeborn, this carbon will experience a different molecular field than this one. The carbon 1s electron will experience a different molecular field. And therefore, they should be located at a different binding energy due to this chemical shift effect. And indeed they are. You can see that they are, this one, the red one come down lower, and the green one come down higher. And what is more powerful is that you can use the area on the curve, right? The area between this should be roughly 1 to 1, right? Because you have one carbon, one red carbon, one green carbon. They should be 1 to 1. And if you can normalize the intensity, you add these together, they should correspond to 2 atoms. So this area should be twice of each of these peaks, because you ultimately you have 2 carbon atoms, right? So they are the same here. They split into 1 to 1 ratio. And finally, just to prove the point, if you have trichloroethylene, what happens? Trichloroethylene, you look at this atom. This is surrounded by carbon, chlorine, and hydrogen, right? Which is the same as carbon, chlorine, hydrogen. So they should occur in the same place as cis and trans. And it is, right? Essentially the same thing. And this atom corresponds to chlorine, chlorine, carbon, as in iso. And they should occur in the same energy as this. So that corresponds exactly right, because that corresponds to what Seeborn is saying is correspond to the different molecular field. Even though you're talking about core shell ionization, you see this different molecular field. Okay, so this is the idea of chemical shift. And chemical shift is powerful, as we'll try to explain later when we talk about electronic structure in nanosciences, particularly because it tells you about the mediates the local electronic environment. So if you're talking about silicon wafer, silicon surrounded by silicon will have a different binding energy. Let's say you're talking about silicon 2p electron, will have different binding energy compared to the silicon 2p binding energy if the silicon is sitting next to oxygen, as in silicon oxide. Okay, so this so-called XPS, X-ray for electron spectroscopy, or as Seeborn would call this, say electron spectroscopy for chemical analysis, called ESCA, right? ESCA, ESCA for chemical analysis, emphasizing the idea of using this electron spectroscopy for chemical analysis. Is a powerful tool. It's a powerful tool to identify what element, what local chemical environment that you have with respect to your material that you see. Okay, so a lot of chemists are using this now to analyze what they got chemically. Okay, so next, so that's the photoelectric effect. So next time when I come back to this, when we talk about the electronic structure, I don't have to go too deeply. Hopefully you remember what I said today. Next, we are still talking about XF. So how does XF occur? We have a photon coming in, this guy into this atom, let's say. This atom completely absorbed my photon. And this photon has enough energy, it ionizes, it go into ionic state, and in the process, it emits a photoelectron. Okay, and then the photoelectron come out. Okay, come out in a wave, like in a spherical wave. I'm just drawing a cut in a 3D format. Think of this as a little sphere emanating from the center of this. So this spherical wave come out from the absorber. I call this absorber. The spherical wave then bounce off from the neighbor atom. Right, like this. So set up a bunch of interference, right, effects. So this scatter back spherical wave from this, and from this, like this, right? This interference effect, it actually perturbs the absorption of my photon. Okay, so this interference, because they are both sort of electronic wave phenomena, your